Now children, let's have a recap of what circles is all about. First we discuss chord properties, children. In case of chord properties, the first theorem is, I'll draw a diagram to explain that. A line drawn from center of circle perpendicular to the chord bisects it. Line drawn from center of circle perpendicular to the chord bisects it. So children, this is a line which bisects this chord perpendicularly. It's perpendicular, so it bisects. It's perpendicular, so it bisects. So the theorem states a line drawn perpendicular from center bisects the chord and its converse, a line drawn from center of circle bisecting the chord is perpendicular to it. A line drawn from center bisecting the chord is perpendicular to it. Then for chords equidistant from the center, if chords are equidistant from the center, means this distance is equal to this distance, children, then the chords are equal. The length of chord AB is equal to length of chord CD if OM equals to ON. So that's equidistant chords are equal. Converse, equal chords are equidistant from center. Let's see some sums based on chord properties, children. The question says, in the figure alongside, OMPN is a square. So children, in the figure, OMPN is a square. A circle drawn with center O cuts a square in X and Y. With center O cuts the square in X and Y. Prove that triangle OXM is congruent to triangle OYP and XM is equal to YP. So children, for this what we'll do first, we'll OXM is not a triangle, we make it into a triangle. OYP is also not a triangle, we make it into a triangle, children. Important things about a square, these two sides are equal. This is right angle, and this is radius, so they'll be congruent by right angle. Hypotenuse side test, that's the first part. In triangle OXM and triangle OYP, OM is equal to OP, angle M is equal to angle P equal to 90 degrees. Property of a square. Second thing, children. Third thing, children. OM is equal to ON radii. Therefore, children, triangle OXM is congruent to triangle OYP. So I write angle hypotenuse test, side test. Once we've got this, children, we can state the second part also. That's XM is equal to YP. Corresponding parts of congruent triangles are congruent. Let's see an example, children, to elaborate this. Question says, children, in the figure, O is the center. O is the center of circle. AB and CD are chords of circle such that AB is equal to AC, OP perpendicular to AB and OQ perpendicular to AC. Prove that PB equal to QC. But to prove this is equal to this, children, for that what we're going to do, first we have this right angle. Second, children, we've been given that PB, we've been given AB is equal to AC. So children, we begin by writing that AB equal to AC given. Therefore, NC equals to MB. And this is by bisected parts of equal chords. Since children ON is perpendicular to AC, it bisects. So this part becomes equal to this and this becomes equal to this. And they are both equal to each other. So this part comes out to be equal to this part. Secondly, children, ON is equal to OM. Equal chords are equidistant from the center. Once we have this, children, we also know OQ equals to OP radii. Therefore, OQ minus ON will be equal to OP minus OM. That's NQ equals to MP. That's, children, this part is equal to this part. That statements above. Therefore, in triangle MPB and triangle QNC, MP equal to NQ, NC equal to MB, statements above and angle M is equal to angle N equals to 90 degrees given. Therefore, children, triangle MPB congruent to triangle QNC. And children, this is by side angle side test. Therefore, QC is equal to PB. And this is, children, by corresponding parts of congruent triangles are congruent. Hence proved. Now, children, let's see the circle theorems. In case of angle properties of circle theorems, the first property states angle subtended by an arc of a circle. An arc of a circle makes an angle. An arc of a circle makes an angle. Makes an angle at center and makes an angle at circumference. So the angle it makes at center and this is the angle it makes at circumference. This angle, children, if this is theta, this angle comes out to be 2 theta. If anywhere on the circumference, children, it can even be like this. But then this angle would still come out to be theta only. So that's first theorem, angle subtended by an arc of circle at center is twice it subtends on same side of the circumference. Should be on the same side, children. Like this arc, for this arc, For this arc, this is the angle center, this is circumference, children. On the same side, this made by this side, this side. It can't be this side and the opposite side. It won't work. It has to be on the same side, children. By this arc on this side and this side. Next theorem states angle subtended by same arc on same side of circumference are equal. Is equal. For example, this angle is equal to this angle, children. This angle is equal to this angle because both are theta. So angles by the same arc are equal. This is equal to this. Next, angles obtained by a semicircle is right angle. So if you ever have a diameter, children, and the diameter makes an angle, the angle definitely, children, would come out to be a right angle, whichever side it is. This will be a right angle, this will be a right angle, this will be a center. Angles by a semicircle is right angle. Next, properties of cyclic quadrilateral. If you've got a cyclic quadrilateral, that means all the vertices are on the circle, all the vertices on the circle. Then the opposite angles add up to supplementary degrees, that's 180 degrees. Opposite angle is supplementary. Opposite angles of a cyclic quadrilateral are supplementary. Opposite angles of cyclic quadrilateral are supplementary, children. And the other property, extended property, exterior angle of cyclic quadrilateral is equal to its interior opposite angle. Exterior angle of cyclic quadrilateral is equal to its interior opposite angle, children. Exterior angle of cyclic quadrilateral is equal to its interior opposite angle. Let's see some sums based on this, children. The question says, in the figure, children, in the adjoining figure, see center of circle, and PQ as a parallelogram. That means, children, this side is parallel to this and this side is parallel to this. Whether we use it or not, we at least need to mark the properties, children. If angle Q equal to 42 degrees, this angle has been given to us as 42 degrees. Calculate angle XRS, angle SCX. XRS, that's this angle, and SCX, this angle. So we need to find out these two angles. Now, first of all, if that's 42 degrees, children, this angle would come out to be 42 degrees. That would be corresponding angles, which will make this angle also 42 degrees since it's angle subtended by the same arc. This arc XS subtends this angle at circumference, this also angle at circumference. So these two angles come out to be equal. And this angle comes out to be double of that. That's 84 degrees since its angle is center. But write it down, children, one by one. Angle Q equal to angle P equal to 42 degrees. This is corresponding angles. That's angle R is equal to angle P equals to 42 degrees. Angle subtended by same arc XS. Therefore, children, angle XCS is equal to twice angle XRS is equal to 84. Angle at center is twice angle at circumference. Let's see some more examples to elaborate this. O, A, P, D, E, C, and this point is F. In the figure, AB is a diameter with center O. Given that EC is equal to ED, an angle EDC equals to angle EDC को 34 degrees. Show that angle CEF is equal to angle COF. Now children, we've been given that ED equal to EC. First we begin by writing that down. So that's EC equals to ED given. Therefore angle ECD equals to angle EDC equal to 34 degrees base angles of isosceles triangle. Therefore children, angle FEC equal to 68 degrees. That's by exterior angle of a triangle. Exterior angle children is equal to sum of remote interior angles. If this is 32 and 32, this will come out to be 64 degrees. And now children, for this being at the center, this arc makes the angle at circumference and this at center. So it will be double children, that will be 64 degrees. Therefore children, FOC is equal to 68 degrees. That's twice of angle FDC. That's angle at center is twice angle at circumference. Therefore children, angle FOC is equal to angle FEC, hence proved. Let's see the example children. Question says, in the figure, ED is the chord parallel to diameter AC. If angle CB equal to 63 degrees, find angle DEC. Now children, if this is diameter children, this will be 90 degrees. This angle comes out to be 63, angle subtends the same arc. This arc subtends angle 63, this angle subtends 63 degrees. So children, this becomes third angle of a triangle. That's 27 degrees. Since the lines are parallel, this will come out to be 27 degrees. Let's write it down children, one by one. Angle CBE is equal to angle CA equal to 63 degrees. Angle subtended by same arc. Angle A is equal to 90 degrees. Angle subtended by semicircle or diameter. Therefore, Angle AEC equal to 180 minus angle AEC plus angle CAE, which is 180 minus 90 plus 63, which is 27 degrees, angles of a triangle. Therefore, angle CED is equal to angle ACE is equal to 27 degrees, interior alternate angles. Actually, a few more sums, children. In the figure, find the value of x. Question says, children, next one. In the figure, CD is parallel to diameter AB. Angle CAB equals to x degrees. Find angle COB, angle DOC, angle DAC, angle ADC. Now children, if this angle is x, it is made by this arc, children. So this angle will come out to be 2x. Angle at center twice angle at circumference. That's COB. Now children, this angle is also x, interior alternate angles. This angle comes out to be 2x, children, again. Angle at center twice angle at circumference. Now children, these two angles are 2x and 2x. This will be angle straight line 180 minus 4x. Angle DOC. Accordingly, children, DAC made by the same arc, DC, children, angle center, angle circumference would be half of it, so 90 minus 2x. So children, DAC is 90 minus x, and now ADC, children, this will come out to be angles of a triangle. This plus this equal to 180, and then we can get this value. So write it down, children, one by one. To begin with, what's been given to us, that's angle CAB equal to x, which is given. Therefore, children, the next part, that's angle COB equals to twice of angle CAB equal to x. That's angle at center is twice angle at circumference. Next, children, angle ACD is equal to angle CAB equal to x, interior alternate angles. Therefore, angle DOA is equal to twice angle TCA equal to 2x. Again, angle at center is twice angle at circumference. Then, children, angle DOC is equal to 180 minus 4x, angles on a straight line. So children, they wanted angle COB, which is 2x, it's one answer. Angle DOC, which is 180 minus 4x, that's the second answer. Angle DAC, children, will be half angle DOC, which is equal to 90 minus x. Angle at center is twice angle at circumference. So children, it's made by the arc CD, at center and at circumference. So the angle would be 90 minus x. And children, angle ADC now would be 180 minus angle DAC plus angle ACD. That's 180 minus angle DAC, which is 90 minus 2x plus x. That's 90 minus x. So 180 minus 90 plus x. That becomes 90 plus x. And that's angles of a triangle add up to 180 degrees, children. So that's your last answer. Now children, let's see some sums on arc properties. In case of arc properties children, the theorem state if arcs in two circles are equal, the angles made by them at the center are equal. If this arc is equal to this arc in length, then the angles made by them at the center are equal. So this angle is equal to this angle. And converse, that's angle subtended by equal arcs in same circle or equal circle are equal, subtended at the center. Converse, if arcs are equal, if angles at center are equal, arcs subtended by them are also equal. Next children, arc properties. If arcs are equal, chords cut by them are equal, intercepted by them are equal. If arcs are equal, chords subtended are also equal. And converse, if chords are equal, then angle at center subtended by them are equal. No proofs required for this children, just apply the theorem. No proofs are required for this. That chords are equal, angles and arcs are equal. And to mix it up children, if arcs are equal, chords are equal, angles subtended by them at the center are equal, and hence the angles at circumference, wherever they are children, wherever the angles are made at circumference, they will be equal. This angle would come out to be equal to this angle because it's made by equal arcs. So this angle at circumference will be equal to this. But you cannot write down directly the theorem children. It's like if this is angle 2 theta, this will come out to be angle theta and theta, therefore they will be equal. We will state step by step to come to that conclusion. Now let's see some sums based on arc properties children. Questions are in the figure. AC and AB. In the figure, AB side of regular 5-sided polygon. AB is of a 5-sided polygon and this is of a 6-sided polygon. AB is a side of 5-sided regular polygon. And AC is a side of regular six-sided polygon. Find angle ASB. Angle ACB. Angle ABC. Now children, for a regular hexagon, see children, the figure continues over here, but they've only shown you one side. The important thing is the angle at center by this arc, by this chord, is 360 by 6, where there are 6 of them. There are 6 of them outlining over this circle, 6 of them. This angle will come out to be 360 by 6, which is 60 degrees. Well, this being equal since it's radii, this angle and this angle will come out to be 60 and 60, which will make an equilateral triangle. Irrespective, the angle would come out to be 60 degrees. Now for a 5-sided figure, that's a pentagon children, the angle would come out to be 360 by 5, that's 72 degrees, with the radii being equal. The angle here children would come out to be 1 and 8 divided by 2, that's 54 degrees and 54 degrees. Now they've asked for ASB, which is 72 degrees, we already got. ACB is half of angle 72, that's 36 degrees. since it's made by the same arc AB, which subtends angle 72 at center and 36 at circumference. Angle ABC children accordingly would come out to be 30 degrees, because angle at center is 60 and angle circumference will accordingly come out to be 30 degrees. Now children, let's write that down one by one. Angle ASC is equal to 360 by 6 equal to 60 degrees. That's angle at center of regular hexagon. AS is equal to SC, radii, also equal to SB. They're all equal because they're all radii, children. Therefore, angle SCA is equal to angle SAC equal to 60 degrees. Base angles of isosceles triangle. Next children, angle ASB equals to 360 by 5. That's for a pentagon. That gives you 72 degrees. Therefore children, angle ACB is equal to half angle ASB, which is equal to 36 degrees, and angle ABC is equal to half angle ASC is equal to 30 degrees. Both of these are children angle subtended at center is twice that at circumference. Friends. Now let's see some sums on tangent properties. Theorems on tangent properties children state for tangents from an external point. First theorem for tangent. A tangent and radius are always at right angles to each other. Tangent and radius to the point of contact are always at right angles to each other. So the point of contact is always at right angles. Children, that's a property of tangent. Next theorem, children. Tangent subtended by external point P. The equivalent length, that's PM is equal to PN. The length PM is equal to length PN. The angle it subtends at the center are equal, and angle it subtends at outside also are equal. These are corollaries, children. These are corollaries. That means you have to prove it. Cannot be taken as a theorem. The only theorem that we've got is first tangent and radius through point of contact are at right angles. Second theorem, tangents from an external point are equal. Then children, this is equal to this. Angle at centers are equal. And this angle is equal to this angle, children, and that's because, and that's by corollary, children. So every time we use it, we have to prove that theorem. We cannot use it directly, children. After that, children, we've got the other theorems for tangents. If two circles touch each other internally, the point of contact lies on a straight line drawn joining two centers, which are just corollaries. And if two circles touch each other externally, the point of contact lies on a straight line drawn joining two centers. Now, children, the next theorems we have on tangent properties. If two chords intersect externally, the product of the lengths are equal. That's PA into PB equals PC into PD. But children, remember it's PA into PB, the whole thing, not just a part, is equal to PC into PD. Not this part, children. CD and AB are not a part of it. CD and AB are not a part of it. Please remember that, children. If they intersect internally, children, if the chords intersect internally, again the same conclusion comes in. That's PA into PB equals PC into PD. But remember, children, it's PA into PB equals PC into PD, like that. Then, children, if it's tangent and external point chord from this point P, then children, the condition is, this is PAB, this is PT. Condition is PT squared is equal to PA into PB, and that comes by similarity. Children, all these theorems come by similarity. All of these theorems, children, come by similarity. Please remember that. The next one, alternate segment theorem, children, which is most likely case for any theorem being asked to be proved. For any theorem to be asked to be proved, it most likely would be this theorem, which states alternate segment theorem. For which the shortcut is TCASA. TCASA, children. TCASA stands for tangent, chord, angle, segment, and the angle it makes. These two angles are equal, children. These two angles are equal. Tangent, chord, angle, segment, and the angle made by that. Or we can take, children, tangent, chord, angle, segment, and the angle it makes. That's this, by this segment. So these two angles are equal, children. These two angles are equal. Now let's see a few sums based on this. Question says, for example, in the figure A, B, D, C, and this point is X, such that AB equal to 4 centimeters, BX is equal to 6 centimeters, XD equals to 5 centimeters. Calculate the length of CD. So we take this length as X, children. AB has been given to us as 4, BX is 6, this is 5. So children, by the theorem that we've got, that's XA into XB equals to XC into XD. XA, children, is 10, XB is 6, which is equal to XC, which is 5 plus X, into XD, children, which is 5. This cancels with this to give you 2. 12 is equal to X plus 5. Therefore, children, X comes out to be 7 centimeters. That's the length of CD. Let's see another example, another question, children. Question says, children, in the adjoining figure, PQ equal to RQ. They've given a diagram like this. So children, the question says, in the figure, PQ is equal to RQ, angle RQP equal to 72 degrees, PC and QC are tangents, PC and QC are tangents, circle with center O, the angles obtained by chord PQ at the center, the angles obtained by the chord PQ at the center, that's this angle we need to find out, children, and angle PCQ, PCQ. So that's calculate angle POQ, angle PCQ. Now children, since this side is equal to this side, this is a right angle here, tangent radius property, tangent radius property. Base angles, children, of this would come out to be accordingly 72, so this would be the remaining 108, so it's 54 degrees and 54 degrees, because of which, children, this angle would be double at circumference, so it would come out to be 108 degrees. Now children, we got 90, 90, and this is 108, so children, this angle accordingly would come out to be 72 degrees. It has no relation with this, children, but they are equal. It's just a coincidence. They have no relation as such that they bear directly between them. Now write it down one by one. First we begin with RQ is equal to RQ is equal to PQ given. Therefore, angle QRP is equal to angle QPR equal to 54 degrees, base angles of isosceles triangle. Once you've got that, children, therefore angle QOP equal to 108 degrees, which is twice angle R. Angle at center is twice angle at circumference. Once we have this, children, angle OQC is equal to angle OPC equal to 90 degrees. It's tangent radius property. Therefore, angle C equal to 360 degrees minus angle OPC plus angle OQC plus angle POQ. That's by angles of a quadrilateral add up to 360 degrees, which gives us 360 minus 90 plus 90 plus 108. That's the difference comes out to be 72 degrees. So children, the angle we needed to find out was POQ, which is 108, and angle C, which is 72 degrees. Let's see an example of this kind, children. Question says in the figure, PT touches circles with center O at R. Diameter SQ meets PT at P. Given angle SPR equals to X degrees and angle QRP equals to Y degrees, prove angle OSR equals to Y degrees and write an expression connecting X and Y. Now children, if this angle is Y, by alternate segment theorem, tangent, chord, angle, segment, angle, this angle comes out to be Y, and since this is radii, this angle would come out to be Y. So angle ORS comes out to be Y, children. Now children, this angle comes out to be X plus Y, and this angle is 90 degrees and this angle is Y. So these three angles, children, accordingly add up to give us angles of a triangle, and that will be a relation connecting X and Y. So one by one. First children, angle QRP is equal to angle OSR is equal to Y degrees. Alternate segment theorem. Children, we applied it like this: tangent, chord, angle, segment, and the angle made by the circumference I equal. Then children, we got OR equal to OS equal to OQ radii. Therefore children, angle ORS is equal to angle OSR equal to Y degrees, base angles. That's the first part, children. That's the A part. For the B part, children, angle QRS is equal to 90 degrees. Angle subtended by semicircle is 90 degrees. Once we get that, children, we state angle OQR is equal to x plus y. Exterior angle of a triangle, that's x plus y, is equal to this. This angle is equal to this plus this. Once we get that, children, therefore in triangle QRS, x plus y plus 90 equals 180. That's angles of a triangle. Therefore x plus 2y is equal to 90 degrees, children. That's angles of a triangle, and that's the relation connecting x and y. Thank you.